Let's dive into some examples of using SVM, specifically support vector classifiers, or SVC. So again, if you haven't already started up your Jupyter Notebook, open up your Anaconda prompt, cd into your course materials directory and type Jupyter Notebook, and navigate into section 8 of the course materials and open up the svc.ipynb file. And here we go. So we're going to again use our example of trying to predict whether your car should be driving fast or slow based on your distance to a bump and how big that bump is. So again, we will generate our fake training data in exactly the same manner to keep all of our comparisons between these different algorithms fair and square. Go ahead and generate that and take a look at it just like we did before. So again, we are looking at the distance to a bump normalized on a 0 to 1 scale here on this axis, and the size of the bump again normalized on a 0 to 1 scale on this axis, where we have slow and fast classifications indicated by the color of each individual point here. What we're trying to do is use an SVC model to try to predict whether a given point should be slow or fast, just given those two measurements of how big a bump is that it's approaching and how far away you are from that bump. Let's see if SVC does a better job. So as with most machine learning models in scikit-learn, it is super easy to actually use them in practice. All we have to do is import from scikit-learn the SVM package. And from SVM, we can call SVC, specify the kernel you want. Remember, there are different kernel types. We'll start with linear. There's another hyperparameter called C that we can set there, and by default, it's 1.0. And we will train that using our entire data set. All of our feature data is in X. All of our label data is in Y. Again, the labels are just fast or slow. The features are distance to the bump and how big the bump is. Very quick to build that model up. Let's actually plot the predictions here and see what it looks like. So SVM does take some more time. It is a very complicated model, so you'll notice that this is actually chewing on that for much longer than it did in other model types, but it is done now. And at the end of the day, we just ended up with another line. So, very similar to what we got with logistic regression, which is a much simpler approach. And because we are using a linear kernel, the most we can hope for are these linear divisions between our data. Let's actually see how you can actually use this model to predict given individual points. I've never shown you that before, but you can actually call predict on any of these models given a set of feature data. So I can just say svc.predict if I want to find out whether my model thinks that if I'm 30% distant from the bump and it's a bump of 30% height, should I go fast or slow? Turns out I should go slow in that case. And for a prediction value of 0, 1, which would correspond to, I end up with a prediction of 1. Let's actually use k-fold cross-validation so we can compare this to our other techniques. And hey, it actually did pretty well here. 84.24%, pretty much comparable to what we got with logistic regression, but actually a little bit higher. So maybe this extra complexity actually did some good. It turns out that SVC does a really good job of finding these classifications. So that more sophisticated model can result in better accuracy. So far, it's definitely a contender for the best model to fit this data. But we did talk about the importance of hyperparameter tuning in our lectures, so let's do some of that. Now I warned you that the RBF kernel in particular is very prone to overfitting if you set your gamma value for it too high. So gamma is an example of a hyperparameter associated with SVC. So let's try playing with RBF. And if that makes sense, let's see if we can tune the gamma value to get better results. So let's start by assuming that RBF can handle this case very well, and we'll just try to converge on the best gamma value. So to do that, we're going to use something from scikit-learn called grid search CV. That's grid search cross-validation that exists within the model selection package of scikit-learn. So this makes it easy to experiment with different parameter values for a given algorithm and try to find which one actually fits the data best. So we're going to set up this param_grid dictionary that maps feature names, feature parameters that are in our model to a list of values that we want to try out. So this dictionary is saying that we want to try out this list of values for the gamma parameter. And I could actually have multiple parameters that I want to set here as well. Now the problem, of course, is that as you start to get more and more features that you're testing at once, you end up multiplying those different combinations together and they can blow up very quickly and end up with a very large number of combinations that you need to test. So in this test, I'm just going to test a specific list of gamma values and see which one works the best. Let's go ahead and run grid search CV with the RBF kernel this time, and we're going to specify this parameter grid that I defined here of these different gamma values. We're going to actually test that with 10 different folds and see what comes out of it. Obviously, that will take a little bit of time, and when it's done, we're going to print out the best params and the best score. So that's going to give me back the list of the ideal parameter values that it found from that list of gamma values and the score that was achieved with it. So when that's done, we'll take a look at the results. Turns out that the best choice turned out to be 0.5 for the gamma value, and that gave me a score of 84%. So it seems like we can't really do much better than we did with the linear kernel here or with logistic regression. Seems like 84% is about the best we can do with this data set so far. But we did converge on the best gamma value to use, so let's go ahead and see what that looks like. And there we have the graphical results. You can see it's more or less a linear relationship. I think if you squint, there's a little bit of a curve there in that line, but not very significant really. Maybe we gained one little data point of accuracy there that we didn't have before. But it looks really close to a linear kernel, right? So maybe RBF is overkill for this problem. Let's try a linear kernel instead, because that might be a better fit for this data. And with a linear model, the hyperparameter that we want to try tuning is called C. So let's try the same trick here, but this time we're going to use a linear kernel, and we're going to have this param grid that maps the value C to this list of different values that we want to try. And usually you want to try sort of like these order of magnitude differences here to try to converge on the right one. So you can see I went from 1 and I tried doubling that to 2, and then I tried 3, and then I kind of like went up to 10, and then I went to 100, then I went to 1,000. So in practice, you'll kind of like start to converge on the best value here. Maybe if you found that the value that came back best was 100, I would then want to try running this again to see if maybe 50 is good or maybe 500 is good, and just kind of do this sort of binary search to try to converge on the best parameter there. Let's kick this off and see what comes back. So again, we're trying a linear kernel with this list of different C hyperparameters, and we're trying to tune our hyperparameter to the best value for actually fitting the data that we have. Turns out that C came back as 0.5, and again, the best score we could achieve was 84%. So again, that seems to be the upper bound of how well we can do on this particular data set. And a linear model did it just as well as an RBF kernel. So given that linear is simpler, if I have the choice between a simple model and a complex model that gives the same results, I'll go with the simple model. And by that same logic, I should probably stick with logistic regression. Anyway, let's visualize that as well, just for completeness. We'll actually plot out that linear model with a C value of 0.5. And I can pull that out with a saying C equals grid.bestParamC to actually extract that best value of C there automatically. And let's take a look at it. And there we have it, just a line again, and there's no curve happening there at the end, but apparently this fits the data as well as anything, so there you have it. It looks pretty much identical to the RBF kernel with that small gamma value, but this model is simpler, and again, simpler is usually better, so we'll go with this one for now. So we'll choose a linear kernel with a C of 0.5 as the winner from our particular exercise here as the best kernel and the best parameter within that kernel.